Hello everyone, and thanks for watching Edupedia World Videos. This is the second video in the topic of magnetometers, and in this video we will study the deflection magnetometer. Now before I start the studying of that device, I'll just like to recap two formulas which we've already studied, and they are for the magnetic field of a bar magnet at broadside on position and ends on position. So if we have a bar magnet minus small m minus capital M, length is 2L, and from this center we take a distance d away and we calculated the magnetic field at this point. It was in this direction, and its magnitude without the dipole approximation came out to be mu naught by 4 pi 2 capital MD. Capital M is 2 times small m times L divided by d squared minus L squared whole squared. And then for the dipole approximation, we'll ignore L in comparison to D, and it will be mu naught by 4 pi 2m by d cube. But for the case of deflection galvanometer, D will be comparable to L, so we'll not use the magnetic dipole approximation. Then instead, if you take a distance d in the broadside on position, the magnetic field would be towards the left, and it would have a magnitude equal to mu naught by 4 pi m by d squared plus L squared to the power 3 by 2 without the dipole approximation, right? So these are the two formulas we'll be using in our study of the deflection galvanometer. So the construction of a deflection galvanometer is quite simple. We have a tape on which we can measure lengths, so it will have markings like a meter tape like this, and we can measure lengths. And then we'll have a compass needle which can rotate about the vertical axis, right? And this will be the compass needle. Now there are two specific positions in which a deflection galvanometer can be used, and they are called the tan A position and the tan B position, right? And the difference between the two positions is how the deflection galvanometer is oriented with respect to the horizontal magnetic field of the Earth. So the tan A position is what we'll study first, and in that case this is north, this is south, this is east, this is west, right? We know the horizontal component of magnetic field will be from south towards north. In the tan B position, we shift this 90 degrees, and this length strip will actually be in the north-south direction, right? So right now this is the case. These markings will be 90 degrees, these markings will be 0 degrees, and these markings will be 90 degrees. Always 0 degrees will be along the horizontal magnetic field of the Earth, which is in this direction, right? That means if there is no other magnetic field present, the deflection in the needle would be 0 degrees, and it would point in the this direction. This is not the vertical direction, this is just the north-south direction, right? So what we'll do is we'll keep our bar magnet here, and for this bar magnet, the magnetic field at this point would be calculated by the ends on position, and the magnetic field would be towards the right, right? So in equilibrium, the magnetic field of the Earth would be upwards BH towards the north, and the magnetic field due to this bar magnet would be towards the east, and it would have a magnitude B, right? And the equation would be B by BH is equal to tan theta, right? Or B is equal to BH tan theta. And we know what B is equal to. B is equal to mu naught by 4 pi 2 MD by d squared minus L squared whole squared, and this is equal to BH tan theta. From that, the result we can get is M by BH is equal to 4 pi d squared minus L squared whole squared divided by 2 mu naught d, and there's a tan theta. So this is it. I told you with the deflection galvanometer we would be able to measure the horizontal component of, we would be able to measure M by BH. Remember, the oscillation magnetometer gave us M into BH. The deflection magnetometer gives us M by BH. We can measure small l by measuring the length of the bar magnet. We can measure D by actually measuring this distance. That's why there are markings present on this. Mu naught is a constant, and theta we can measure as the deflection in this case. right? So the deflection will tell us what the magnetic field due to this is, because we've kept this deflection magnetometer. Oh, I'm so sorry. This should be deflection magnetometer. I apologize for that. Galvanometers measure currents and voltage differences. We've seen them before, right? So anyway, our goal is complete. In this case, this is called the tan A position, and in this we are able to measure m by bh, and this is the formula. This is the formula which you should remember. Now let's look at the tan B position. In the tan B position, this would again be the north, south, east, west direction, but now we'll keep it like this. I'll not draw the complete thing. I'll just draw it like this now, right? And again, north south is always 0 0. This is always 90 90. So if there is no other magnetic field present, the needle would be pointing in this direction. If there is a magnetic field present, it will be pointing in this direction. This is theta, such that tan theta will be B by BH. Right. Now in this case, we'll put a bar magnet like this, and now it will be the broadside on position which will experience the magnetic field. So the result will be B is equal to mu naught by 4 pi m by d squared plus L squared to the power 3 by 2, and this is equal to BH tan theta. From that we get m by BH is equal to d squared plus L squared times 3 by 2 into 4 pi by mu naught, right, into tan theta. So we can measure m by bh in two separate ways, either in the tan A position or the tan B position. Now what we can also do with a deflection galvanometer is something which is called using the null method. And in that, we don't have to measure m by bh separately. We can directly compare the magnetic moment of two bar magnets. It can be done either in the tan A or the tan B position. First I'll show you the tan B position because we've already drawn that on the figure. So we take one bar magnet. In this case, if the polarity is, let's say, this, actually for this kind of deflection the polarity would be like this. In the other case, we take a polarity to be completely opposite, like this. So this will create a magnetic field towards the right, this will create a magnetic field towards the left. Right, and we keep on adjusting the distances d1 and d2 until the magnetic field is completely vertical. That is, these two magnetic fields completely cancel each other and the needle is pointing in the vertical direction. In that case, what we'll get is the two magnetic fields will be equal. So mu naught by 4 pi m1 by d1 squared plus l1 squared to the power 3 by 2 is equal to mu naught by 4 pi m2 by d2 squared plus l2 squared to the power 3 by 2. And from that what we get is m1 by m2 is equal to d1 squared plus l1 squared to the power 3 by 2 by d2 squared plus l2 squared to the power 3 by 2. So not only can you measure m by bh, but again, if you just know the magnetic moment of one bar magnet, you can calculate the magnetic moment of any other bar magnet directly. The same thing can be used in the tan A position. This is called the tan B position, by the way. And there are two differences. In one difference is these arms, meter long arms, in the first case were along east-west, now they're along north-south. And the second difference is the bar magnet was parallel to these arms. In the tan A position, it is perpendicular to the arms in the tan B position. If you do the same method in the tan A position, the null method, then the relationship you'll get will be m1 by m2 is equal to d2 by d1 times d1 squared minus l1 squared whole squared by d2 squared minus l2 squared whole squared. Right, I'm not going to write the whole thing. You can obviously see that directly. In that case, one bar magnet is like this, the other is like this. They have opposite polarities and they push the magnetic fields opposite to each other such that they cancel out. This has to be only applied after we've created a d1 and d2 such that the needle is in the vertical direction. Right, so we can measure two magnetic moments, or we can measure the ratio of the magnetic moment of one and the magnetic field due to the earth. Another thing a deflection galvanometer is generally used for is to compare the magnetic field of the earth horizontal component at different points. So for example, if we use just this formula and D and L and everything is kept the same, and we perform it in two different locations, in one location we would have BH1 and the deflection would be tan theta 1. In the other location we would have BH2 and the deflection would be tan theta 2. Everything else is the same, so the equation is BH1 by BH2 is equal to tan theta 2 by tan theta 1. So we can also measure the horizontal component of the Earth's magnetic field at two different locations using this deflection galvanometer. Now what happens once you've got MBH and M by BH? MBH can be written as Y, let's say, and M by BH, let's say you calculate that to be equal to X. Then you can multiply these and the final result you'll get is M is equal to root of XY. Right, you multiply these two, M square is equal to XY, M is equal to root of XY, and B is equal to root of Y by X. So if I just use these formulas for the tan A position, that is MBH will always be the same oscillation magnetometer. M by BH I measure using the tan A position. Then once I have applied these two formulas, the result I get is M is equal to, and I would like you to calculate these and actually verify the result for tan A position and then do it for tan B position as well. If your tan A position answers match my answers, I'm sure you can get the correct answer for tan B position as well. It will come out to be 2 pi times d squared minus L squared by T. T is the time period in the oscillation magnetometer, root of 4 pi by mu naught I tan theta by 2d. Right, I is the moment of inertia, right? And the magnetic field horizontal component will come out to be, this is root of xy, this is root of y by x, and that will come out to be 2 pi by t times d squared minus r squared whole squared root of mu naught by 4 pi 2 id by tan theta. Right. Now I know a lot of students who actually remember these two formulas, but there's really no need to remember these two formulas as long as you remember the values of x and y. Right, because very rarely are you going to have a question in which you'll be given all of these values and you need to find out this value. Questions, especially in IIT-JEE, will be somewhat more complicated, and they're not testing how well you can remember formulas. They're actually testing your understanding of the subject. Right. Now there's one very small final thing which is slightly off topic, which I'll just say here, and it's called Gauss Law for magnetism. Actually, Gauss had nothing to do with this law, but it's generally called Gauss Law because students remember Gauss Law for electricity, and this is somewhat similar. We know that magnetic field lines always occur in loops, right? Magnetic monopoles do not exist. That's why magnetic field lines never start and end at any point. Well, that simply means that the closed integral of B dot ds, that is the magnetic flux, is always 0 through any surface. Integral E dot ds was Q enclosed by epsilon naught. But since there is no magnetic monopole charge, it will always be magnetic dipoles which have a net magnetic moment of 0. Integral B dot ds over any closed surface will be 0. This is just a manifestation of the fact that there are no magnetic monopoles in nature. You cannot have a single magnetic monopole. So this completes magnetometers. Thank you.